Hi guys, in this video I want to explain why adding the capacitor to this circuit causes charges to stop flowing and prevent the bulbs from turning on. And in so doing, hopefully refine our understanding of just why charges flow in general in a circuit. So to start off, I'm going to remind us of what we talked about in our electrostatics unit. This is a positive charge. Just imagine like a lot of positive charge perhaps. The field lines are pointing away from it, because if I put a positive charge anywhere around it, it would feel a force outwards. Whereas a negative charge, if I were to put a positive test charge anywhere around it, it would feel a force towards it. So those are the field lines kind of radiating outwards. And what I've highlighted here in dotted lines is areas where if I put a charge here versus if I put a charge here, they would have the same electric potential energy. The way to think about potential energy is like how much energy you would get from that particular charge arrangement. And so it doesn't matter really whether you put the charge over there or over there. They both have the same amount of sort of energy in that configuration. And because we define electric potential energy relative to positive charges, then we can think of these areas next to a positive charge as having like a lot of electric potential energy for a positive charge. So that's why we call it an area of high potential. Potential is another word for voltage. Like those are the same thing. Those are equivalent ideas. So when we were talking earlier about sort of surfaces of equal potential, try to making analogy to topographic maps, areas next to a positive charge had high height. And you can see, if you sort of visualize each line as a certain elevation, then this is a high height, this is getting a little bit lower. The further out you go, the lower the elevation. And it's kind of the flip for when you're near a negative charge. So if you put a positive charge over here, it doesn't have much room to accelerate over. So there's not too much energy associated with this location. But if you were to put it out a little bit farther, there'd be more room for it to accelerate over. You can get more energy out of that arrangement. The farther and farther you get from a negative, the more energy you would get from that arrangement. So the topographic analogy, going with that, areas next to a negative are kind of like these sinkholes, these bottomless pits. So if you were to visualize sort of a positive and a negative, next to each other, one would be like a really high height, and then the negative would be a really low height. And so I think that's the first part of our how to think about circuits. Areas of lots of positive charge, high height. Areas of low or of lots of negative charge, low height. And basically just building on that, the more positive charges you have in a location, the higher the height. Just going with that. So what does that have to do with circuits? Well, a positive end of a battery, you can think of it as it's like a lot of positive charges, and the negative end of a battery, a lot of negative charges. Something I wanted to say here is, though I'll be talking in terms of movement of positive charges, because our analogy depends on, it's all relative to the movement of positive charges. Electric potential energy is defined relative to a positive charge, and electric potential rather is defined relative to the energy that a positive charge would have, basically just thanks to Ben Franklin. I'm going to be imagining just conventional current, the flow of positive charges. The reasoning should work opposite. It's just it works good with my analogy over here of positives being high height and negatives being low height. Okay, so areas of lots of positive charge are high height, high elevation. Areas of lots of negative charge are low height. So this can kind of help us explain already like why charges flow. If I have, let's say if I have only one battery in the circuit, let's say one battery is like one positive charge amount, then I'm going to get a certain amount of flow across these two light bulbs. This is a light bulb. If I add another battery, to my circuit, there's an even greater difference in height. So I'm going to get even more flow. And why am I getting flow? It's because like when I have an imbalance in height and I put a charge there, it's going to want to go from high to low. That's like the power of this analogy. So the second thing that I'm trying to suggest is that the greater the difference in height, the greater the flow of charge. Another way of saying this is really Ohm's law. V equals IR. When you have a greater difference in height, that's voltage, voltage being electric potential. So the greater the difference in height, the greater the charge flow. So current is sort of like charges flowing up through a point per second. So that's your current. So the greater the difference in voltage, the greater the current. Like that's just Ohm's law, but we can kind of apply that here to understand what's going on with the capacitor. So number one, when I have a bunch of batteries, somewhere along the line, the height decreases, right? This is a high height, this is a low height. The batteries maintain that. And if you were to go and measure it with like a voltmeter, you would see that if this was at, let's say, 10 volts, and this was at 0 volts, like a height of 10 and a height of 0, that this value is going to be somewhere in between. Assuming that these bulbs are identical, then the difference in height between them is going to be also identical. So that at this point, everywhere on this wire would be at 5 volts, like the same height. So what I want you to visualize is like plus, 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 plus. It's not a perfect analogy. Sorry, those should be bigger. But this is actually kind of what's going on under the hood. Like if you were to look at the charges, charges would sort of be bunching up over here. And as they pass through, this bulb is acting like a kind of a roadblock. And so there's the same amount of charges passing through, but it's just like sort of at a lesser height. Again, the difference in the height corresponds to how much charge is flowing through it. So over here, they're at the same height. So it's not to say that charges aren't flowing here, but it's like there's a lot of charge flow over here. We basically imagine that wires have no resistance. So this is almost like a superconducting highway. I don't want to dwell on that though, but the key idea here is like you're losing height along the way, and a light bulb is just like a roadblock. It's not doing anything to the charge. It's kind of just impeding it, and as the charges hit the light bulb filaments get hot, give off light. That's the whole trick. All right, that's all like what's happening in a regular circuit. Now, so what happens when we add a capacitor? You can think of a capacitor essentially as just like two giant metal sheets, just with an air gap in between them. And the thing that you should know from circuits is like if you have a gap anywhere in your circuit, charges aren't going to flow across that circuit. So that still holds with the capacitor, right? There's essentially this gap. But what you should see in the video, I'll link it in the description if you didn't see it, that when you hook up this capacitor, there is charge flow, but for only a moment, a few seconds. So what you are seeing is charges flow for some reason, and then charges stop. If you were to disconnect the battery and then connect the capacitors just to the bulbs, there would be charge flow, again, just for a few moments, and then it would stop. So if you just go with thinking about the capacitor, and if you were to hook up just the capacitor to the bulbs, remove the battery from the circuit, the reason it was able to cause those charges to flow, like what makes charges flow, it's the difference in height. So there had to have been some difference in height in the capacitor. And let's kind of zoom in what happened. Initially, when you connect the batteries to the bulbs and the capacitor, there's this difference in height. Like this is all medium height. This is like a low height. This is a high height. Before you connect the battery, everything's sort of at neutral middle ground height. When I connect this high height to this lower height rather, charges are going to flow because it's like a lot of positive charge, no positive charge. So you're going to get that charge flow. So charges are going to flow. And what you're going to have is, oh, look, a positive is building up here, but it can't go any further. And whereas over here, you have like this neutral ground and like a really low sinkhole. So you're going to get charges flowing from here to the negative end of the battery. And so, if movement of positive charges, if a positive charge is going to go from here to here, this is leaving it overall negative on this plate of the capacitor. There is no movement of charge between the plates of the capacitor. It's only like on the two ends of the capacitor that charges are flowing. So this is happening in like 1 second, and then the next second, more charges are going to flow. The difference in height here is less. That's the key idea. The moment a charge has flowed, now there's like one charge. So the difference in height here is like 4 units to 1. So the difference in height is 3. So less charges are going to flow. And that's why you're seeing the bulb be less bright, because less charges are flowing. When more charges build up, charges are moving over here. So there's like this charge difference, this height imbalance. Now what's the charge flow? After charges have flowed, there's a lot of positive charges here. What's the difference in height here? If this is 4 units and this is 4 units, then this area is also 10 volts. It's like trying to get a ball to roll on level ground. It's not going to happen. And actually, the charges started here and they started to build up the height over there to the point where they're at the same height. And similarly over here, this started out at a neutral middle ground. The negative end of the battery was like a sinkhole. And so this height lowered until they were now the same height. And now what happens? So after you get that charge flow, it decreased, so the bulb got less dim and less dim until it stopped flowing altogether. Now, if you disconnect this bulb from the battery, I have a height difference here. So I can hook up, if I close this circuit, now I'm going to get charges flowing. Again, movement of positive charges, high height, low height, I'm going to get flow of charge. You could measure it with if you were able to measure the flow of actual charges, you'd see that the direction changes now. Before it was going, this way, now it's going the other way. So that's kind of what's going on under the hood. The other thing I want to just highlight is this doesn't, when you hook up the capacitor to the bulbs, one charge is going to move, and then that height difference is going to go away. And that's why the bulbs start off bright, and then they start to dim. Another charge moves. And now the difference in height here between the 10 volts and the 0 volts is getting less. And then less. Bulbs get dimmer, and then less. To the point where there's no difference in height, in electric height at all. So this really is underscoring what the battery is doing. The battery isn't just causing there to be, charge flow. It's maintaining that height difference. There's some chemical reaction going on inside that's maintaining this difference in whatever, 1.5 volts. In the case of a chemical battery, it's a chemical reaction. In the case of your outlet, it's power from the grid that's maintaining that difference in electrical height. So that's why capacitors can store charge up momentarily. That's why if you're ever taking apart like some kind of electronic device, you do want to discharge a capacitor. Any capacitors in there, otherwise you might get shocked. But a battery is like a continuous source of energy, and that's what makes it different than just like 2 parallel plates. That's kind of what's going on. Hopefully that was helpful. Just to summarize, the key idea here is lots of positive charge is like a high height, lots of negative charge is like a low height. And when you have a difference in that height, you're going to get flow of charge. The greater the difference, the greater the flow of charge. All right. Hope that was helpful. Take care.